Hello, how are you doing? It's Mike here, and in this video we're going to discuss the relationship between polar coordinates and your rectangular coordinates. Basically, we're going to discuss the conversion from polar to the xy plane. And remember, polar falls in the form of r comma theta. So we want to go from the polar coordinates to the xy plane. So very similar in some of our prior discussions, we discussed the relationship to go from from parametric to our xy plane, then vice versa. We can also discuss how to go from polar to the xy plane. We are not going to delve into how to go from polar directly to parametric, so you do not have to worry about that in this sense. So it's important for us to be able to go between both polar and then our xy coordinate plane. It's very important for us because we have to rapidly convert sometimes. So we will recognize here that this here is considered the positive x-axis, on our xy plane, and this is our polar axis in our polar plane. So we're going to recognize that we can go from one to the other by basically lining up our polar axis to our positive x-axis. So be very cognizant of that. This is designed for Calculus 2 course. So I'm just going to go ahead and just do a reminder on how to convert between polar and the xy plane. So our x value can be defined and calculated by taking your value of r and multiplying it times cosine of theta. And the y value can be determined by taking the value of r and multiplying it times sine of theta. So let's just go ahead and look at any value here. Sorry, not what I wanted. Well, there we go. So we'll say we're looking at this point right here. Here we have our value of theta. Actually, we'll do our value of theta here. So it extends up to pi over 3. So if I were to drop down a vertical axis here, and if I were to extend this to be here, we could see that we have a 90-degree right triangle, with this being our angle theta. Theta, by definition, can be defined several ways, but most specifically, sine of theta is your opposite, So that's why we can define this as r sine of theta, and r cosine of theta will be the value of the x portion of the xy coordinate plane, because cosine is your adjacent, and this is going to be our adjacent leg, and this guy is going to be our opposite leg. And that can help us transform this from the polar plane to our xy plane. Again, this is a value of r, that's the radial length that exists from the pole to the point itself. So another great equation that we can use is that we can define r squared being equal to x squared plus y squared, and this is just our Pythagorean theorem, where we can relate the two sides of the triangle to the hypotenuse. And then lastly, we know that tangent of theta is equal to your opposite over your hypotenuse, which is just going to be a value of y over x. And we could also rewrite tangent of theta as r cosine of theta over r sine of theta over r cosine of theta. And notice the r's cancel, we get sine over cosine, so we get tangent again. So this is another way for us to rewrite all these different relationships. So now, since we define these relationships and how to calculate them and go back and forth between polar and your xy plane rectangular coordinates, let's go ahead and try some examples. So let's go ahead in this example. Let's find the rectangular coordinate of the point P, whose polar coordinates are r theta equals to 6 comma 2 pi's over 3. So we'll look at this as being an example. So we just want to convert from polar. So we're going to convert from polar, and we're going to go to our xy plane. So what I like to often do is that I like to often draw just to give myself an idea of where I am. So here we can imagine this being circle radius 1, circle radius 2, 3, 4, 5, 6. So this is going to be coming somewhere here. And 2 pi's over 3, 2 pi's over 3 is going to be approximately right here. So we know that this point is going to be in quadrant 2. So this helps me tremendously. This helps me tremendously just identifying where I want to go and where this point is. So we're looking for this point right there at 6 comma 2 pi's over 3. And this angle here between the between the polar axis and our terminal side is going to be a value of 2 pi's over 3. So first thing that I want to do is I want to calculate my x and y values. So I know that my r is equal to 6. And my theta is equal to 2 pi's over 3. So x is equal to 6, we'll just define it as r cosine of theta, which is going to be 6 times cosine of 2 pi's over 3. And cosine of 2 pi's over 3 is negative 1/2. Remember, cosine is negative in quadrant 2. So we're going to have negative 1/2, so we have a value of 3. We have a value of, it's a value of negative 3. And we expect this to be negative because we're going to the left of the y-axis. So we're traveling on the negative x-axis. So that makes sense. So we get a value of negative 3. So now we expect our y value, our y coordinate to be positive because we're above the y-axis. So this will be r sine of theta, which gives us 6 times sine of 2 pi's over 3. And this will be 6 times square root of 3 all over 2. And this is 3 square root of 3. So therefore, the rectangular coordinates of P are x comma y, and this equals to negative 3 times 3 square root of 3. So that's how we're able to convert from our polar coordinates to our rectangular coordinates. So we have negative 3 comma 3 square roots of 3. I think this is very easy, very plug and chug, nothing too complicated. So hopefully we're really enjoying this and not find this too complex. So let's go ahead and try another one. Let's go from polar coordinates and let's calculate polar coordinates given rectangular coordinates. So let's go the opposite way. So we want to calculate, or I should say determine, not really calculate, well you do calculate to determine them, the polar coordinates of the point, we'll call this P, whose rectangular coordinates are, let's do negative 2 comma negative 2 square roots of 3. So again, I want to graph this just to give myself an idea of where we are. So here I am at negative 2 and then negative 2 square roots of 3, which is going to be a value slightly larger than 3. So we are approximately down here, and this is negative 2 comma negative 2 square roots of 3. So we need to figure out exactly how to get to this in terms of our polar coordinates. So first of all, we define our polar coordinates. Our polar is going to be equal to r comma a value of theta. So I know that for r tends to be the easy one because we can use the Pythag identity and recognize that r squared is equal to x squared plus y squared. So knowing this, I know r squared is equal to negative 2 squared plus negative 2 square root of 3 squared. Negative 2 squared is a value of 4. Negative 2 squared is also 4 times 3 is a value of 12. So this gives me 16. this implies that r squared is a value of 16, or we'll just say that r equals to plus or minus 4. So be very careful. Remember we talked about this in our prior videos. We can define this point into polar coordinates with both a positive value of the radius of the radial length and a negative value of the radial length. So we do have two different situations coming up here, but that's okay. We're okay with it. So now we know our value of r is going to be a value of 4. So now we have to figure out our value of theta. So our value of theta we can determine by knowing that tangent of theta, so tangent of theta is equal to our value of y over x, and our value of y here is going to be from here to here, and this is negative 2 square roots of 3. This distance here is going to be negative 2 square roots of 3. So this will be negative 2 square roots of 3 over our value of x, which will be from here to here, negative 2. And this equals to tangent of theta, which then implies that tangent of theta equals to positive square root of 3, or theta is equal to tan inverse of square root of 3. So I'm sure some of us are going right to the fact that tan inverse of square root of 3, we're thinking this theta is equal to a value of pi over 3. Because tan inverse of square root of 3 is pi over 3. But remember, pi over 3 is right here. So that is pi over 3. We have to be careful because we are not naming pi over 3. We are naming pi over 3 all the way down plus pi revolutions to our terminal side, not the extension of our terminal side. So let's think about this now. If we wanted to name the value of r, given that this angle is pi over 3, we're going to have to use the negative r value. So we know our first point we can define as pi over 3, with pi over 3. But if we use a positive value of r, we're going to end up in quadrant 1. Clearly we want to be in quadrant 3, so we're going to have to use a value of negative 4. Negative 4 comma pi over 3. Also, if we want to use the value of our positive radius, that will give us a value of 4, but it will be plus 3 pi's over 3, which is going to be 4 pi's over 3. So we can name this with a positive radius and a negative radius. But remember, we said that there are infinite ways to name points. There's infinite ways to name points. We can add 2 pi times n revolutions to both this value and this value, and we're going to arrive at the same point. So we must clearly define this point as being negative 4 pi over 3 plus 2 pi times n, where n is an integer. Or we can define this point as positive 4 comma 4 pi's over 3 plus 2 pi times n, where n is an integer. Because this will allow for every different amount of iterations, 1 revolution, 2 revolutions, 3 revolutions, negative 1 revolutions, negative 2 revolutions, negative 3 revolutions, and so forth. So we have to describe this as an infinite amount of solutions, and we're safe about that, and we feel comfortable that we've described every single possible way to describe this one point that exists here in quadrant 3.